Great. So welcome to the last part. We are almost done. And so far, we have covered a lot of material that you would need to be able to work with deep learning. And hopefully, by now, you are comfortable with a lot of concepts and also with a lot of tools that you have in PyTorch, and hopefully by now you have hopefully by now PyTorch is as familiar as NumPy for you, right? And as you have seen, you can do everything very easily with PyTorch if you read the documentation, and that's it. That's basically the basics of how you do deep learning. Now, what I want to tell you today is about reading papers, because you might think, I'm not going to do research on deep learning. I don't even care about research in deep learning. All I need is to be able to use the tools that I need to do what I want to do with deep learning, right? And so then why everything that Xiang said matters? Actually, deep learning is so. Can I close the door?
Yes, please.
Thank you. So deep learning is moving so fast and is evolving so fast that unlike traditional areas of technology, that you have something solid that you just learn it from a book and the rest of it is for you to go and repeat whatever you have learned 100 million times in 500 different jobs and companies. Deep learning is very different. This is evolving rapidly every day. So where does that appear? In the papers, right? And the papers, and then you have a billion papers published every night. So if you're like me, following everything that is happening in different areas of deep learning, from images to sound to video to NLP, using NLP, you'll go crazy, because every morning you have tons of stuff, and there are two things that you need to be very good at, and you need to get very good at if you want to be successful at deep learning, which is what you want, because you're here and we are spending this time together, which shows what your objective is. So A, you need to be able to separate noise from signal in the papers, right? So every day you get tons of papers. Only a small fraction of them are actually relevant. So you need to train your natural neural networks to separate what matters from what doesn't. And then the other one is to be able to read the papers and then get what you want, all of it, without spending weeks on it, right? And that comes with experience and with a little bit of training that I was hoping to create that experience for you is reading, exploring, discovering, testing, and finding the right tools for yourself. Okay? We'll talk more about it in 2 hours. All right. So today, what we are going to do, we will talk about the mathematics of finding the solution. And so we talked about the mathematics of building the structure, the architecture of deep learning in the first session. Then we talked about the mathematics of extracting information from data. We did it last time. We saw how doing convolution and building convolution on neural networks are built on top of layers that will help us extract information from data and then process them to get to where we want to get to. And then today, we want to talk about that last piece where I have my architecture, I have built my layers, and then they are doing what they have to do. They are extracting information and sending it forward. Now, how do I find the weights, and how do I find the optimal weights? As we saw, this is all about weights and biases that we have to learn. How do we find them, and how do we do it? How do we optimize on that to solve our problem? All right. So that's the idea. And before that, we are going to have, is Willie online? Willie is online? All right. So Willie has this really nice visualizations that he will walk you through to help you understand the convolutional neural networks even better. As we saw, interactive or active visualization is very important in understanding something. And I hope one of the take-home messages from our from the 9 hours that we spent together during the last 3 weeks has been that if you do something, visualize it, and then that will help you build a much better business than if you do something amazing and put it in a table. One of these tables, if you know, if you go to a meeting with customers or stakeholders and executives and you put up tables and words, us humans are very bad at reading stuff. Words and numbers are a nightmare to us. You can ask yourself. But if you use the same information and visualize it, and if you make it interactive, or if you make it an animated visualization, you go from being ignored to being super valued and being supported, and you can build, you will be much more successful. All right? So that's a little career advice I had to tell you. Now let's move on to the ConvNet visualization. And I hope, we haven't tried this. This is the first time we're going to try that. I hope the sound works well. Willie. Sorry. Willie is going to
You decided not to do it.
All right. The visualization.
Yeah.
Okay. All right. Then forget everything that I said. we are not going to have that. We will talk about the things here. So, how do we solve the problems? When we you have seen this, and you have seen it in statistics. You have seen it whenever you were fitting any curve to a bunch of data points, and also this is the intuitive way for us how things work. We start with something simple, right? And a great example is, how do you date someone, right? You start with an experiment and you screw up, and then you think about it with a broken heart. What did I do? What went wrong? And then you go back, you start from the beginning, and then you change. You don't radically change what you do. You just change. You say, I'm good, everything was going well, and then I made this mistake here, so let me fix that. So you fix one thing at a time, and then you go and it lasts longer, and then again you fail, and then you go back, right? So hopefully that's how it works. And then after a few tries, you converge, and you're successful, and you will be living together happily ever after. So this is exactly how our neural networks learn as well. But here we are dealing with, and this is something that you should understand very well. We have a cost function, we have a loss function that has some weird shapes, and we want to minimize our loss. All right, that is equivalent of finding a solution. When we say my problem is solved, that means, for example, I have a bunch of cats and dogs, and I say, all right, who remembers what is the objective function that we talked about in the first session for a classification problem? Yes. And so what precisely do we have there? Cross. Yes. So cross entropy log likelihood is what we usually use for classification. And what we want to minimize is the number of times I confuse cats and dogs, right? So I want to get them right. Now, so I want to minimize my number of mistakes, and that's my problem. So I'm minimizing something always, and that thing is usually a measure of my error. If I'm working with, by the way, where is Reza? He was supposed to tell us everything about text today. All right.
Still working on it.
If you're online, we haven't forgotten. So if we are training a language model, what we are learning is what is the most probable word that comes after these words in this sentence, in this context, right? So basically, we have a measure of error, and then we have some parameters here because we have parameterized our model. And for example, in the convolutional neural network, we saw that the parameters that we are using are the values of weights in all those convolution layers that we need to learn. We start with something random, and then we learn the values, right? And how do we do it? There are different ways of doing it. We will talk about one of them, and I can just briefly mention some other ways of doing things. But basically what we do is that we start from somewhere, and we say, I start from here. I look at the derivative of my curve to see which way it is tilted, and I keep rolling down the hill until I get to the point where it is flat, and that gives me the minimum, right? Now, what are the dangers here? One of them is that the problem doesn't have a minimum, right? Let's assume that we are living in a good world and our problems have a solution. So forget about that one. Another danger here is, you see we have 3 points where I get a flat, and they are like the lowest points here. These two are called local minima. This point is called the global minimum. All right. We have to make sure that we are not stuck in a local minimum, because we can do better. The error, because this one artificially is telling me that I found it. We are at the minimum, but we are not, because there is the actual solution is here. All right. How do we make sure that this happens? I will tell you. Remind me in 20 minutes if I didn't talk about how to make sure that we are not getting trapped in local minimum. And that's it. So basically, we take a derivative, we move with the in the direction of derivative, and we take steps that are given by how large my derivative is, how large the gradient is. If I'm somewhere with a huge gradient, I will take a big jump here. If I'm somewhere that has a small gradient, I'll start taking smaller and smaller steps. And how do I know I have converged? If the problem has converged, I see that I'm taking many rounds, and I'm actually not moving much. That is a good sign. That is telling me that I have taken 10 steps and I haven't moved much, which means that the gradient is so small that it's not moving me anymore. All right. So these are some useful information to have. The gradient is, and by the way, all the white slides, I have taken it from a really good course that is called Zero to PyTorch. No, PyTorch from Zero to All, something like that. Is a very good course. There are some YouTube videos and slides available. These are all available for free. All right. So basically what we want to do is that we have a loss. We have the value of the loss that I can plot versus the size of my parameter, and I want to minimize that. What you need to remember is that, so here we will talk about, we will work with a problem, with a sample problem, which is simple because we want to be able to solve it in a few minutes. But usually these are this dimension. This could be a 6 million dimensional space. Like AlexNet, I think we talked about it last time. That, if I remember correctly, that has about 6 million dimensions. All right. So we have a space that is really large, and the function is a very complicated landscape, and we want to move along this landscape until we get to the bottom of it and find the minimum. So we have to be very efficient. Plus, if we are lucky, we will have tons of data. And that introduces another problem of how to deal with this stuff. And we will talk about some of these problems. So the gradient, when we talk about the gradient, that means taking a derivative with respect to our parameter. If you're familiar with d loss over dw, and this looks strange, this is basically, we are using this because this notation, who is not familiar with this notation? Should I even explain it, or should I skip it? All right, so very briefly, I'll tell you. When you do df by dx, if you use d, that means you basically have one parameter and you're taking a derivative with respect to that, all right? But sometimes, which is in most cases in deep learning, you have more than one parameter. And when you say, I want to take a derivative of this function, the natural question would be, with respect to what? Taking a derivative means you want to see how the function changes as you change a parameter. Now, do you want to do it with respect to x or y? All right. And if you imagine a two-dimensional case, that means, do you want me to keep y fixed, and then change x and see how the function changes with that, or do you want me to keep the x fixed and then look at the differences of the function as I change y? All right. So that's that. But basically, every time you see that, it's telling you I'm taking a derivative. That's it. And then when I compute the derivative, I start from a random place, completely random place here, and I say I have no idea where my minimum is. I start from a random point, and I compute the value of my derivative at that point, and then I update my parameter, which means I move in the direction of, I move downhills in this way. I compute the derivative multiplied by a learning rate. This can be something between 0 to 1. And then I subtract it from my current value of the of the parameter. All right. So that's basically what it means. Is that I'm moving down. All right. I'm going in this direction, and as you see, alpha is fixed. Let's say it's 0.1. All right. It's one parameter that we just pick it randomly, not randomly. We pick it to be small, and it's called the learning rate. And as we go down, the derivative gets smaller, which means that I will be subtracting smaller values from W, which means I will be taking smaller and smaller steps. And when I get close to the minimum, to the absolute minimum, the derivative becomes almost 0, which means that I will spend time pretending to take steps to go forward, but actually nothing happens here, and that's how I know I've converged. All right, yes?
Can you just briefly mention how you get alpha learning rate?
Alpha is,
Question?
so how do we pick alpha? Picking alpha is an art, and so let's see what happens. Is. And so let's see what happens here. If alpha is very small, right? If alpha is very small, we will be moving very slowly, right? So if alpha is small, my steps will be very small because whatever the value of the gradient is, I will be multiplying it with a very small number. All right. So my steps will be very small. This is like you have climbed Himalayas, and you want to go back home, and you're taking baby steps to go back home. All right. So this is sure. So you will be safe, but it will take you many years to get done, right? So that's, let me finish that. So that's the disadvantage of very small learning rates. If alpha is big, you will be making big jumps, and you might miss your actual minimum, and then you will take again another big jump, and it won't let you, it will make you miss your point, and then you will be jumping around because you just don't see it. All right? How we pick it, go watch Fast AI, the first 2 courses, videos is free. You can watch it, and it's very watchable and nice. And you will see some tricks on how to do it. But basically, we pick something between 0.1-ish or less. For our example, let's look at the example. You'll see how it depends on the problem. Yes.
I was going to ask, so in regards to stochastic gradient descent, does it still apply to a 2D plane like this?
Yes, it can, and we will talk about it. Any more questions online? Questions online? No?